Okay, hello, here's another step maths video, and just for a change today I'm going to look at a question from the most recent paper, 2012. So if for some reason you prefer not to look at those questions, maybe if you're planning to use them as a mock exam, then don't look at this video, but I guess the the title of the video gave that away. However, if you do want to look at it, maybe just for a change, look at a more recent example. Here is one such. So this is the sixth question from the first paper of this summer's exam. And before I start, I should mention that my impressions, just having gone through this paper yesterday, what I noticed about it was a marked, no, to be fair, I don't think I'm imagining it. There is a definite higher emphasis on what I would call technical algebraic skill. Most of the pure questions, and indeed by the looks of it, some of the mechanics questions, required quite a lot of algebraic working. It's interesting that they chose to do that. I'm not quite sure why, or whether it's just an accident. But if you do look through the questions, you're going to find the same. I think that that kind of skill, detailed algebraic working, is emphasized more. Now that's partly true in this question I'm going to look at, but this question is well, yeah, it is true in this question, but it's not the only thing that's important about this question. So let's read it, and of course you probably will notice that the quality of what you're looking at on screen is not very good, because this is a scan, not an original PDF, because it hasn't yet been released on the website. So that's why it occurs to me I really ought to just read out the question for you in case you can't see it clearly. So it says, a thin circular path with diameter AB is laid on horizontal ground. A vertical flagpole is erected with its base at a point D on the diameter AB. The angles of elevation of the top of the flagpole from A and B are alpha and beta respectively. Both are acute. And the point C lies on the circular path with DC perpendicular to AB. And the angle of elevation of the top of the flagpole from C is phi. Show that cot alpha cot beta equals cot squared phi. So we'll do that first part of the question first, but if you're planning to just do the whole question yourself before looking at the video, let me briefly read the rest. It says that show that for any p and q, cos p cos q sine squared 1/2 p plus q minus sine p sine q cos squared 1/2 p plus q is equal to 1/2 cos p plus q minus 1/2 cos p plus q cos p minus q. Then it says deduce that if p and q are positive and p plus q is less than or equal to pi over 2, then cot p cot q is greater than or equal to cot squared half p plus q, and hence show that phi is less than or equal to 1/2 alpha plus beta when alpha plus beta is less than or equal to pi over 2. Okay, so that's the full question, but we'll now start to look at the first part. Okay, let's dive in. So we had a situation where there was a circle. Let me try and draw a relatively big circle here. I hope that will be recognized as a circle using the little trick there. Yeah, is that a circle? More or less. I hope it's big enough. So there's a circle, and we're going to mark points A and B such that AB is a diameter. So let's say that's A, and somewhere around there is B. Let's draw the diameter as some kind of straight line here. That's good enough, I guess. And then we're going to choose another point. Now, what was it now? Yeah, D. Another point D on the diameter. Obviously, it doesn't have to be in the middle; can be anywhere. Anywhere on the diameter there. That will be D. And then we choose C such that DC is perpendicular to AB on the circle. Okay, so let's draw that as a blue line as well. Okay, so CD and AB are perpendicular, and you have to imagine that this is a plan view looking from above. Maybe I'll just write plan view. And the flagpole is erected at D, so that the top of the flagpole is directly above D in this diagram. Now, we're given certain information, so we can't draw... actually, let's have a side view. Because I'm trying to explain this answer, I'm going to draw a little bit more detail, maybe something like this, with this being D, this being A, this being B, and this being a point E, the top of the flagpole. Oops, flagpole. Oops, tagpole that is apparently. Yeah, it's a flagpole. Oops. So we can already see quite a few right angles here, right? DE is perpendicular to the plane of ACB, the circle ACB. So that's a right angle. That's a right angle. And there's a couple more right angles, right? On the plan view, this is a right angle because CD is perpendicular to AB. This is a right angle. And finally, maybe drawing another couple of lines. I hope you recognize that there's another right angle in this picture. It's here. Because, so we could say angle ACB is 90 degrees because AB diameter. So a basic fact about circles there is going to help us. Okay, so seeing all these right angles suggests to us what? It suggests to us that we can use Pythagoras Theorem, at least sometimes, and indeed that will be the key to proving the given relationship. What we're required to prove, if you remember, was cot alpha cot beta equals cot squared phi. Cot alpha cot beta equals cot squared phi where the angle, if I remember correctly, the angle alpha is here, the angle beta is here, and the angle phi I have not shown. It's let's make a third diagram, D, E, and C, and that would be phi. Those are the angles of elevation, meaning the angle from the horizontal to the line to E. So we're required to prove this. Okay, how do we go about it? As I said, Pythagoras Theorem suggests itself because of all these 90-degree angles. So how does Pythagoras Theorem relate to these cotangents? Well, consider any one of these three triangles here, ADE, BED, and DEC. This distance, this vertical distance, we might call x, for example. That's the same, DE. Well, cot alpha is x over AD. I'm sorry, it's the other way around, isn't it? Tan alpha is x over AD. So cot alpha is AD over x. Cot beta, by the same token, is dB over x. And cot phi is dC over x. Okay. Now we know that AD plus dB is AB. And we can use the right angle triangle ACB to construct this equation. AD plus dB squared, being the hypotenuse of that triangle, is equal to AC squared plus CB squared. So you see what I'm doing here is I'm trying to use Pythagoras to make the connections between the lengths on this plan view, because I recognize that the height x appears in all these terms, so it will be irrelevant. In fact, we could just write x equals 1 without loss of generality and we'll just get the same answer. But that doesn't really matter. So having written this, obviously I can expand this out. The left-hand side can be expanded as a square into AD squared plus DB squared plus 2ADDB. And that's still equal to AC squared plus CB squared. But, excuse me, but I also know that AC squared can be found by examining the triangle ADC. So in that triangle, AC is the hypotenuse. So this AC squared on the right-hand side could be rewritten as AD squared plus DC squared. Sorry, we can't somehow keep the diagram in the picture there. So I'm doing AD squared plus CD squared equals AC squared. So that's AC squared, and CB squared is the hypotenuse of this triangle, so that's CD squared plus DB squared. And now we see the result is going to come out, because so looking now at this equation, the left-hand side there and the right-hand side over here, AD squared plus DB squared cancels, so therefore I get 2AD DB equals CD squared plus DC squared. Well, that's the same as CD squared. Therefore ADDB equals CD squared. Therefore AD over x, going back to the cotangents, times dB over x equals CD squared over x squared. Therefore cot alpha cot beta equals cot phi squared, which was required to be proved. So, you know, don't be intimidated here by the fact there's 3 dimensions. It's not uncommon for geometry and mechanics questions and so on to have some 3D element to them. But the 3D element here is quite simplified, because it's not as if we have to examine some kind of tetrahedron. We've just got several right-angled triangles all connected together. And so we just exploit Pythagoras Theorem to get the required result. So hopefully you found that fairly easy. Now the next part. The next part is this very long equation. It says show that for any P and Q, and I'll read it one more time, although it's going to... Actually, I won't read it another time because I'm going to write it in a minute. This very long equation, we've got to show that it's true for any P and Q. Now it's worth just quickly looking at the rest of the question to see the context. So then it says that deduce that if P and Q, those numbers already mentioned, are positive, and P and Q obey a certain relationship, then cot P cot Q is greater than half cot squared half P plus Q. So we immediately see there that that equation, or that inequality, has a very similar form to the equation we just proved. So it seems pretty obvious that what they're asking us to do is prove a certain identity and then use that identity to verify that we know something about the relationship between cot alpha, cot beta and cot squared phi. So this second part of the question is entirely new. It's a very long equation and we have to prove it. Now this can be quite intimidating. First thing I'm going to have to do is copy it all out, and I think I'll spare you the pain of watching me write it. I'll just pause the video and write it. Okay, so I've written out the whole equation there. Yeah, equations of this length and complexity can really put you off, but they don't always need to. This is an identity. They're telling us it's true for all P and Q, so we should just be using trigonometric identities. Now, which trigonometric identities do we know that might connect to this? Well, you should know things like cos A plus B, sine A plus B, and there are related identities, of course, for cos 2 theta or cos and sine 2 theta, which are obviously connected to that, or special cases of it. Now, how can we use these? For example, should we start from the left-hand side or the right-hand side? That's not such an obvious question, is it? It's often a good idea to start from the most complicated side and try to work to the simpler side. In this case, we could say the left-hand side is a bit longer, so is arguably a little more complicated than the right-hand side. But that's not totally convincing in itself. Another thing we can observe is what are the arguments of the cosine and sine functions. Let me identify what I mean. Here we have p and q arguments. Here we have the argument half p plus q, p and q again. Here we have the arguments p plus q and p minus q. So focus your attention on those. Here we see that not all the arguments are the same. We've got arguments of 1/2 of p plus q on the left, which is significantly different from p plus q on the right. So how would we be able to transform from either p plus q to half p plus q, or from half p plus q to p plus q? Well, the answer is you think about theta and 2 theta, don't you? How do we transform between those? You could think of this as a half theta maybe, but obviously that's the same thing. So if we think of these two angles as theta and 2 theta, then this is theta, this is theta, this is 2 theta, 2 theta, 2 theta. Now these p and q here, of course, are sort of components of that. So that's not entirely clear, but it's suggestive because you know, when I looked at this, I was certainly intimidated by it. I think anyone would be, you know. But I thought, well, the object that I can most easily convert into something simpler is probably this one here, this half p plus q. Well, I've got sine squared theta and cos squared theta, and I know certain very famous formulas for converting them into 2 theta. So if I convert them into 2 theta, well, it must be the case that the right-hand side would come out. So what are those famous formulas? Of course, I mean the formula sine squared theta is 1/2 1 minus cos 2 theta, and cos squared theta is 1/2 1 plus cos 2 theta. And that's already very encouraging, because it means that I'm going to get terms of the form cosine 2 theta, which is cosine p plus q, in both cases, and indeed the right-hand side only contains cosine p plus q. So the last bit of tidying up will be to see how to fit in these cos p, cos q, sine p, sine q. Now, if you went in a different direction, you know, it's quite possible you might have got the right answer, either quickly or slowly. I don't guarantee that my approach is the only one or the best one, but it certainly makes sense. So what I'll do is take the left-hand side and treat the sine squared and cos squared terms using those identities we just mentioned. So here we go. All right, left-hand side, this is going to take a lot of writing, equals cos p, cos q. Now, sine squared half p plus q, that must be equal to 1/2 1 minus cosine p plus q, minus sine p sine q. Now I've also got 1/2 1 plus cosine p plus q, because p plus q is twice half p plus q. Oh, how many different brackets have I got here? 3 brackets. Now, let's take out the terms that don't include the cosine p plus q. Well, that means we've got 1/2 cos p cos q minus sine p sine q. Do you recognize that? You certainly should recognize that. And the terms which include cos p plus q look like this. They're all negative, minus, and they've all got a half, and then they're cos p cos q cos p plus q, oops, and they're sine p sine q cos p plus q. And now we see it's all going to come out, because here we've got 1/2, so that's equals 1/2. This is cosine A cosine B minus sine A sine B, so this is cos p plus q. And here we can take out the factor cosine p plus q, which is common to both terms in this part, and then we've got cos p plus q, cos p cos q plus sine p sine q, which of course is cos A cos B plus sine A sine B, which is cos A minus B. So this gives us the right hand side. Cos p minus q. So that's the same as the right hand side, which was to be shown. Okay, no problem. Are there other ways to do it? To be honest, I'm not sure. If you start on the right hand side and expand out, you get a lot of terms, especially in this product cos p plus q cos p minus q, that expands out with lots of sines and cosines. So I think it might be a lot more awkward if you started with the right hand side, but I'm quite happy to be wrong about that. You know, it's true of a lot of step questions. As long as you get to the answer reasonably quickly, it doesn't matter too much whether you've chosen absolutely the best way. Now let's look at the next part. If I can find it. Where is it? There? No, sorry. I've forgotten where the question is. Where is the question? It's a bit stupid of me, isn't it? Let me just pause the video and try and remember where. Okay, sorry for that. Here's the question. Deduce that if p and q are positive and p plus q is less than or equal to pi over 2, then cot q is great. Okay, so we're going to have to use what we've just proved to get to a form like the one we had in the beginning of the question, to make this connection. So the form we had in the beginning of the question, cot alpha cot beta equals cot squared phi. So we want cot p cot q and cot squared, on the right hand side, cot squared p plus q, I think, yeah. Okay. So let's look at this long equation. How do we get cot p cot q? Well, here we've got cos p cos q, and here we've got sine p sine q. So it doesn't take a genius to figure out, well, let's divide by sine p sine q. But on the right hand side we need cot squared p plus q. So again we're going to have to divide by cot sine squared half p plus q. That would give me, hold on, let me just look at the original thing again. Yeah, so we're definitely going to have to divide by sine squared half p plus q, as well as sine p sine q. Oh, I'm sorry, I totally forgot the point. Yeah, yeah. So now I remember. So if you look on the left-hand side, it looks very promising, because we want cot p. Let me write it here actually in the right form. We're looking for cot p cot q, and I think it was greater than or equal to cot squared half p plus q. Let me just double check I got the sign right. Yeah. So that's what we're looking for. Let me mark that out in a different colour. That's what we're aiming at. And we can see the left-hand side looks almost exactly the same in as much as there's a difference. And if we divide by sine p sine q, we get cot p cot q, and if we divide by sine squared half p plus q, we get cot squared half p plus q. So that looks right. The problem, of course, is there's also a right-hand side. So if indeed we divide and it's true that this part is bigger than this part, it must be because this part is positive. So what we've got to kind of verify is that that's positive. So let's see if it works. Again, there's quite a lot of writing out to do here. Let's call this equation star. Yeah, so in this part there's a fair amount of writing but not much thinking to do. So that equation right at the top is star. So I'm going to take star divided by, I have to write fairly low down here, I hope that's okay. Divide it by all the terms sine p, sine q, and sine squared half p plus q. What do we get? We get cot p, cot q, minus cot squared half p plus q on the left hand side. And on the right hand side we get 1/2 cos p plus q factored into 1 minus cos p minus q. And all of this must be divided by, sorry, I have great difficulty with drawing straight lines horizontally. Divided by, that's better, sine p, sine p, sine q, sine squared half p plus q. Okay, now it's given that p and q are both positive, and p plus q is less than or equal to pi over 2. Therefore sine half p plus q, well, let's just say half p plus q, sorry, did I get that right? P plus q less than or equal to pi over 2. So half p plus q is less than or equal to pi over 4. Which obviously means that sine, well actually what am I saying? That's irrelevant. No, they're foolish. Sine squared of a number is always a positive number. Well, it does follow that p is less than pi over 2 and q is less than pi over 2. So in any case, it's obvious that all these terms are positive. Sine p is positive, sine q is positive, sine squared anything is positive, theta, because if theta is positive, not 0, theta is not 0. And more importantly, cos p plus q, because p plus q is less than pi over 2 but bigger than 0, that's positive. And also 1 minus cos anything is positive, because cos anything is less than 1. So all those terms are positive, therefore right hand side is positive, and therefore cot p cot q is greater than, oh actually are we allowed to include 0? Yeah, we are, because p plus q is less than or equal to pi over 2. Okay, so actually cos p plus q could be 0 if p plus q were pi over 2. So cot p cot q, the right hand side is greater than or equal to 0, cot p cot q is greater than or equal to cot squared half p plus q. Okay, which was to be shown. Yeah, for some reason my page insertions are going in the wrong place. Here. No. Here. Sorry, slight technical problem there. My new pages are going in the wrong place. I've forgotten how to do that. Anyway, so that part was easy in as much as just recognise that the left-hand side looks very much like the given relationship. So just find a way to prove that the other side is positive. Okay. I hope that's reasonable. The last part, if I can find it, yeah, the last part, show that phi is less than or equal to 1/2 alpha plus beta when alpha plus beta is less than or equal to pi over 2. Alpha and beta are positive, so we can apply what we've just learned, and we can say that cot alpha cot beta, so in other words alpha and beta satisfy the conditions for p and q in the previous part, so we can replace p with alpha, q with beta, and we can write cot alpha cot beta is greater than or equal to cot squared half alpha plus beta. And now we also know that cot alpha cot beta is actually equal. We know what it's equal to. It's actually equal to cot squared, cotangent squared of phi. Okay. So therefore cotangent squared of phi is greater than or equal to cotangent squared of half alpha plus beta. Now we notice here that the arguments to the cotangent on both sides are let's say acute, and they're between 0 and pi over 2. So let's just quickly remind ourselves of the shape of the cotangent curve. Whoops, that's terrible, isn't it? Never mind, this case it doesn't matter. The cotangent curve, so the tangent curve goes up like this, so the cotangent curve goes down like that, where that's pi over 2. That's theta, and that's cot theta. Cot phi? Cot theta. Okay, phi. So you notice that it's a decreasing function. Now, obviously that means that cotangent squared has the same basic shape in as much as, in any case, it's decreasing on the interval from 0 to pi over 2. So phi is between 0 and pi over 2, and a half alpha plus beta is also in the same interval. So it's these cotangents are positive, and it's a decreasing function. So the result is kind of obvious. It's just a question of how to write it. Cot half alpha plus beta. So we can get rid of the square. It's clearly true. That's also true. And because it's a decreasing function, of theta, we can just flip the inequality sign, because a bigger theta means a smaller function value. And that is what was to be shown. Just double check that. Yes. So, that's the end of that question. I suppose it's not a really very interesting question, both the first and the second part, excuse me, both the first and the second part might sort of scare you a little bit, depending on what your background is. As you can see, the geometry was as simple as it possibly could be. You just needed to remember that the angle at angle subtended by a diameter is always pi over 2 or 90, and then just use Pythagoras Theorem to relate the various triangles. And the second part is more likely to scare you, which is this very long identity or equation. Let me get rid of that note there. And yeah, as I said, I myself was quite intimidated by that when I first saw it, and I thought, well, this looks like the kind of thing where if you go the wrong way, you might get into terrible trouble. So if you do start on the right-hand side, for example, and try and simplify it by expanding cos p plus q, well, you know, one needs to preserve the flexibility to realize there might be a better way. Don't be too stubborn. If one way looks extremely difficult, you know, step is difficult, but it's not extremely difficult like it would take you 3 or 4 pages of algebra to do something. You know, a typical step question on an A4 sheet of paper, you know, you usually would be able to do it on 2 sides of A4. Maybe 3 sides in other cases, but you know, if you're doing pages of algebra, something's wrong. So, you know, don't be afraid to sort of switch over. At the end of the day, if you know this identity is true, you should be able to pull it out somehow, right? So, as I said before, just look at the arguments. When you've got that and you've figured it out, the rest of the question is by step standards very, very simple. Yeah, this inequality that we've deduced here really comes out immediately from the previous result. And then the observation about phi, alpha and beta is again very trivial. Just use the property of the cotangent function. It's decreasing and it's positive in the interval. So I hope that was of interest to some people, and thank you for watching. See you again soon.